Next tribune is all about graphing trig functions and stating some of their properties, and then getting into how to solve certain types of problems that involve using especially sine and cosine functions. We're going to talk about tan a little bit, but we're going to focus on sine and cosine. Okay? And you will find, like here, actually, let's use Desmos. Relax. I'm going to use it and just show you. So let's just all stay calm. So let's see what sine looks like. There. That's what sine looks like. Okay. We'll see in a second. We'll see why it looks like that in a second. This is what cosine looks like. You're going to find that it's very similar. Like so. It's basically the same graph, except it was shifted a bit. Okay? These are called periodic functions because what they do is they repeat their pattern. So if you look at the sine one, the red one, okay? You guys want to head up? You look at the red one. Let's look at where it starts at the origin. Starts here, curves up to a maximum, comes back down, crosses the x-axis, curves down to a minimum, and then hits the x-axis again. And then notice it starts that same pattern all over again. Starts its same pattern going backwards too. Okay, so this is like one cycle of a sine pattern. And it's just made up of many cycles. So any kind of question that involves anything cyclical, you can solve with sine or cosine. So anything that moves in a circular motion, you solve with sine and cosine. Because if you roll a wheel and graph it, it looks like this one as you roll it. That's just one example. There's numerous examples that we'll talk about towards the end of this unit. But what it also means, so here's one cycle of a sine. If I start on the y-axis, here's one cycle of cosine. Starts at maximum, comes down to the x-axis, bottoms out, back to the x-axis, and reaches its starting point up top again. That's one cycle for cosine. Okay? Because they keep following this pattern, the name we give to them are periodic functions. That's what they're called. They follow the same pattern over certain periods. Another thing that we also refer to them to, and these are sine and cosine functions because they're like a wave pattern, is we call them sinusoidal. Yeah, let's all just remain calm. Let's all just remain calm. Okay. Those are names we specifically give to sine and cosine because they follow a wave. All right, so we saw how they looked, but let's see if we can get that same look. And a lot of times, like last year when we talked about quadratic functions for the first time, we talked about absolute value functions for the first time. We talked about rational functions for the first time. This year we talked about radical functions for the first time. The first step that we always took in seeing what they look like, table of values. So instead of the x-axis, we're going to call it the theta axis, because it's going to represent the angle measure, and this is in radians. And then this would be the y-axis. So here's where your knowledge of the unit circle comes in. It's the sine of 0. Well, here's 0. Okay, it's 0. So there's our starting. Now remember, we did pi over 6, we did pi over 4, we did pi over 3, but we're going to jump to pi over 2. Okay? What's the sine of pi over 2, which is up here? 1. Now we're going to jump here. What's the sine here? 0. Then we're going to go down to 3 pi over 2. -1. And then we're going to come back where we started and complete the cycle. So just to graph this, I'm going to put a notch for pi over 2. I'm going to put a notch for pi. I'm going to put a notch for 3 pi over 2. I'm going to put a notch for 2 pi. So every notch on the theta axis or the x-axis, we're going up by a half pi every time. So like this is a half pi, 1 pi, 1.5 pi's, 2 pi's. And then here, it's either going to be 0, 1, or -1. All right, so we said pi over 2 was 1. The sine of pi is 0, so pi comma 0. The sine of 3 pi over 2 is -1, so 3 pi over 2 comma -1. And the sine of 2 pi is 0. And we can see that we've graphed one cycle. Okay? And that cycle would keep repeating itself as we go to the right forever. And it would keep repeating itself as we go to the left forever. And it would keep repeating itself every 4 notches, where 1 notch is half a pi. So this is just one period or one cycle of sine. It continues forever. So we want to go like this to indicate that that cycle is going to continue to the right forever. We can even go into the negatives. Negative pi over 2. Negative pi. Negative 3 pi over 2. And negative 2 pi. And it follows the same pattern. So it goes down to here, and then up to here, and then up to its maximum at 1, and then down to here, and then it continues to the left forever. So there we just graphed 2 cycles of sine. And there's certain properties that we look at, certain properties that you're familiar with, like domain and range and intercepts. You guys know about those. But there are some other properties that we talk about specifically relating to sine and cosine. Okay. First off, before I go to amplitude, I want to talk about what a midline is. And a midline is a horizontal line that splits sine or cos graphs into two. Where would the horizontal line be that would split this into two? Equal above, equal below. Where would I draw the horizontal line so that it would split this in half? Sorry? This axis, right? That would split it in half. So that's the midline. So now that we know what the midline is, we can get the amplitude. And the amplitude is simply the distance, always positive number, okay? The distance from the midline to the maximum or the minimum, because it'll always be the same, because we split it in half horizontally. So the amplitude would be the distance from the midline to here, which is 1, right? Because this is 1. Or I could see an amplitude over here. Remember, it's the distance, so take the absolute value. The distance is 1, not -1. Amplitude is always positive. So these are amplitudes. So in this case, our amplitude is 1. Can you see what could we do to the graph? What could we do to the graph to change the amplitude? What would you do to change the amplitude? Sorry? Stretch it, which is something that we've done. Okay. So if the amplitude was 2, that's taking the amplitude of 1 and stretching it. If the amplitude was 1/2, that's the same as stretching it in or compressing. Okay. The period. It's the length of the interval, horizontal, that it takes to complete one cycle. So how long does it take to complete one cycle? Well, if we're going to start a cycle here, it finishes here, and then it starts again. So this here would be the period. Well, what's the length from 0 to 2 pi? 2 pi. A lot of times, period will be in terms of pi. Sometimes it won't. Now, these other ones, you're pretty familiar. So looking at this graph, what's the domain? Negative infinity, positive infinity. Or theta is an element of the real numbers. Either one is fine. You don't have to know both. What's the range, lowest to highest? Including both. So remember, we write the lower one first. So -1 to +1, including both -1 and +1. Or y is greater than or equal to 1 and less, sorry, greater than or equal to -1 less than or equal to 1. What's the y-intercept? Well, you just have to look at the graph. 0. The zeros or the x-intercepts, remember this, you guys, because you could see this on your mock midterm. Zeros means the same as x-intercepts. So if you're asked to find the zeros, you're asked to find the x-intercepts. Well, this is a little bit more challenging because there are infinite x-intercepts. We've only graphed 5 of them. Like here's an x-intercept, here's one, here's one, here's one, here's one. And if we go to the right forever, we're going to keep hitting. And if we go to the left forever, we're going to keep hitting. So what we can do is we can say, okay, I know that there's an x-intercept at pi, right? The next one to the right, I add another pi, 2 pi. The next one would be at 3 pi. The next one would be at 4 pi. If I go backwards, take away a pi, 0, then negative pi, then negative 2 pi. So how can I show positive and negative using fancy notation? KEI. So the x-intercepts, I'm going to say, all right, we're going to start at pi. And we're going to add 1 pi, add 2 pi, add 3 pi, minus 1 pi, minus 2 pi, minus 3 pi, or add k pi, where k is an integer, or z. Talked about that on Friday. Don't really have to worry too much about the x-intercepts of sinusoidal functions. Okay. All right. Let's look at cosine. So again, we saw what it looked like when we used the Desmos graphing calculator. Very similar to sine, a wave-like pattern, but just shifted slightly. So again, let's use our unit circle and start a table of values. What's the cosine of 0? 1. What's the cosine of pi over 2? What's the cosine of pi? Negative 1. What's the cosine of 3 pi over 2? 0. And then we're back to 2 pi, which is 1. So notice we go 4 notches again. And every notch is half pi, or pi over 2. So this is pi over 2. Add another half pi, and we get 1 pi. Add another half pi, and we get 3.5 pi's. Add another pi, half pi, we get 4.5 pi's, or 2 pi. Still at 1. Still at negative 1. Except this time, remember with sine, we started at the origin. Okay? Or we started, like normally we start our cycle on the y. When you graph these things, always start on the y-axis. So for sine, on the y-axis, it was when theta was 0. But this time, with cosine, it's going to start up here. And then it's going to follow the same pattern. It's going to come down and hit the theta axis, or the x-axis. And then it's going to go further down and bottom out at negative 1. And then it's going to come back up to the theta, or x-axis. And then it's going to return to its original starting point. And of course, they go on forever. So we could go into the negatives, we can continue going on to the positives, but that's one cycle of cos. So sine starts in the middle, cos starts up high. And let's just look at the properties again. So the midline is here again. That's the midline. So what would the amplitude be? 1. Same as sine. Amplitude would be 1. What would the period be? How long does it take horizontally to complete one cycle? Well, we start here, and then we go down, bottom out, come back, and now we're at our starting point. How long did that take horizontally? 2 pi. Because we started at 0 and finished at 2 pi before the cycle starts again. Domain and range, same thing. As sine theta. So the domain is everything. It goes to the left and right forever. For theta is an element of all real numbers. And the range, lowest -1, highest 1. For y is greater than or equal to -1, but less than or equal to 1. The y-intercept is different. What's the y-intercept? 1. And the zeros, or the x-intercepts, they go on forever. So we got to use that notation. Notice that we use that K, K-E-I, when something goes on forever. Like if we wanted to talk about all coterminal angles, if we wanted to talk about all solutions, if we wanted to talk about all x-intercepts or sine and cos, K-E-I, you just got to figure out, what do we add? Like, do we add a pi every time? Do we add 2 pi every time? Well, here, there's an x-intercept at a half pi. And then the next one to the right is after 1 pi. So pi, half pi, then 3.5 pi, then 5.5 pi. So I'm adding pi in both directions. How do I show both directions? K, where k is an integer, or z. And I'm going every pi. Because this k represents +1, -1, +2, -2, +3, -3, etc. Remember in the last unit, when we were solving trig equations, and you ended up with something like this that you were asked to solve? Do you remember what you got when you solved that? You got an error. Why? Look at the graph. Cosine can't go above 1. Cosine can't go below -1. Boom. Mind blown. That's crazy. Do you see how it's all connected? You all right? How come you refuse to go to your own desk? I'm just wondering. I'm just curious. You think it's fun? You think you learn better back here? Yeah, all right. Okay.